Welcome back. In this video, we are going to look at how we can build a penguin classifier in TensorFlow. And this again is a tutorial in TensorFlow docs, and I'll be directly copying the code from the tutorial example. It's just that I'll be explaining as we go through this code what each line of the code is trying to do. The first thing we need to do is uh, if you haven't already, is to run this line of code, which is exclamation mark pip install tfds dash nightly, and so we'll get the data set in there, and we'll also install the library TensorFlow datasets using pip install TensorFlow underscore datasets. So with this, then let's get, if you've already done this, we can now get started with the actual coding. So first thing we need to do is import the libraries that we need. So let's do import OS, then import TensorFlow as TF, and then we need dataset. So import TensorFlow underscore datasets as tfds, and then we can import matplotlib. Import matplotlib dot pyplot as plt. So we have these. Wondering why we have this red in red here. So import TensorFlow underscore datasets as if, let's run this. Okay, so that's not a problem. And we can also look at what the versions are. So we can print the version of TensorFlow and tfds. So print tf dot underscore underscore version and underscore underscore, and similarly we can print the version of tfds. So tfds dot underscore underscore version, and we have the versions that should come up now. So this is TensorFlow version 2.9 and tfds version 4.6. Now first thing we'll do is preview the data. So here we have preview data, and for this we'll look at some sample of the penguin dataset. ds underscore preview, and the way to do this is, if you are familiar with scikit-learn, we used to use the uh, internal scikit datasets, and it's a similar thing here. We are using the tfds.load, and what inside of this we'll specify the dataset penguins uh, slash simple. So what we are doing here is importing the simplified version of the dataset. So the simplified version, and for the simplified version, then we have we'll use the split is equal to train, and with info is equal to true. So we'll get the information about what the, similar to the description we get in scikit. And once we have this, what we will get is values in here and information in the info part. We can now use that. So if you look at the ds underscore preview dot ds underscore preview, we get an object that you'll see shortly. This is what we get. To convert, we can put this into a data frame, and to do that we would say it's called df is equal to tfds dot as underscore data frame, and within this we put the ds underscore preview, and we take 5 records, and we also get the info of these. Now we can simply look at the df as we see here, and that's how we see it. We can look at info.features as so. As you can see, we have the body mass in grams, Kalman depth in millimeters, length, then flipper length, island, sex, and species. We have all that information in there. In info.features, we have a dictionary which gives the data type. It's tf.float32, etc. for these. Now, the last one, which is the species, that's the target. That's what we are going to predict. And this was a preview of what the data set looks like. Now, points to note is we have number of features we have are 6. So these are the number of features. 1, 2, 3, 4, 5, 6, and the last one, that's our target value. And the target value has 3 classes, as it says here. We have 0, 1, and 2. So 0 refers to, let's put this down here. 0 refers to the class a daily penguin, and then we have the class 1 that refers to chinstrap penguin. So these are the types of penguin, and then we have the last one. There is a this one is called Gen2 penguin, and what we'll do then because we know this, we can put them in class names. So class names is equal to daily. Then we have let's put this inside of quotation marks, and next we have the chin strap, and finally after chin strap we have the Gen2. Okay, so after this we can move ahead and look at a pre-processed data that we will be using for training. So we can pull that down, put it in test and train set, and see how we can work with that. So create, train, and test sets. And for this, we are going to again use tf.ds.load. So the variable we'll use here is ds underscore split info as before, and tf.ds.load. And now within this, we are going to use the dataset penguins, again the same penguins, except that now we'll use the process dataset that is ready for us to train a model on. And we'll perform a split because this dataset doesn't come in a form where the split for 10 and test is already done. So we'll put that inside of these square brackets, and what we'll do is we'll do a 80-20 split. So the first 20 records, so train, and we said the first 20% records, they go for the test set. Then we'll put another rest of the 80%, so train, and then remaining 80%, so those will go in the train set. So this is saying that the colon says that and everything after this is going to be up to 100% that will go in the train set, and this 0 to 20% in this case nothing, means 0 colon to 20% goes in the test set. In addition to this, inside of the load we can pass argument as supervised is equal to true, and that will help us with the training as a supervised learning problem. And next we have info, so we definitely can get the info with this. So let's put with info is equal to true. So this is what we would get, and if we look at df underscore split, let's run this first, and then we'll look at what's in the df underscore split. So if you look at df right here, we have df underscore split, and inside of this what we will get is we have this list. Yeah, and inside of this list we have these two sets of data, prefetched data set element and the shape. We have the shapes in there. What we can do is we can now put each of these into their respective splits by name. So we can say that if we are looking at the split 0, which is going to the first item in the list, let's put that in ds underscore test, and then the second one we can put that in ds underscore train. So let's put that here and say ds underscore train, and this would be then 1. Let's now convert this to a data frame. So we have tf underscore test is equal to tfds dot as underscore data frame, and inside of this we can specify ds underscore test dot take 5 comma info, and same thing here. Next thing we can do is tf underscore train is equal to tf ds dot as underscore data frame, and we can specify ds underscore train dot take 5 comma info. And what we can do is we can, so let's look at what the error is. The name tfds is not defined, and uh, yep, that's because I need to run this again. I had to close the notebook, and that's why I think we'll have to go through this entire run again to get all the cells active. Okay, now we can look at the shape of this, or we can check the what's inside of the df train and test. So this is the df test, and we can, if we print it, print df test, this is what we have. And then similarly you can print df train, and again in this case we have the features. We have 4 features, so we have 4 columns here, and we have the target column species. Let's now create a batch. So we can say ds underscore train underscore batch is equal to ds underscore train dot batch 32. And with this information now, let's go ahead and create the variables feature and labels that we can use later on. So features is and labels is equal to next and iter ds underscore train underscore batch, and we can print the features, print features, print labels, and here we see that these are the features that we have, and these are the labels for each of the records that are in that features. We can take a look at some of these features. So we can create a plot here. To plot the features, is what we can do. We can create a scatter plot, plt.scatter, using the features. So features, and we'll use all the rows from the column 0, and we'll use features, all the rows from column, say 1, and we can use c is equal to labels, and then cmap is equal to viridis, and finally we can add the labels x and y labels, plt.x label body mass, and then we have plt.y label Kalman length lngth, and then we have plt.show. So when we run this, we should see a scatter plot. X and y must be of the same dimensions. So yep, that was a typo there. And when we run this, this is the plot we see, and we can change the features that we are trying to plot. If we plot the feature at index 2, we see this plot right here. So now what we'll do is we'll move on and look at how we can build a simple linear model in this project. Before we build a model, let's look at why we need a model. And model is essentially a relationship between the features that we have in the data set and the labels. So model would have the weights associated with each of the labels, and together the mathematical formulation would be a model that helps us connect the features with the labels with it. So if we look at the penguin classification example, in this case, the features that we have are the measurements done on each of the penguins, such as the body mass, culmen depth, flipper length, and culmen length. And the labels would be the type of penguin that is there, ideally chinstrap or gentoo. And so essentially the model would be a mathematical formulation that would be able to connect the features to a specific type of penguin class that we have. And here are the pictures of the penguins from Wikipedia. We have the Gentoo, Adelie, and Chinstrap. And the differences are, I think, based on, of course, the features that we have in the dataset, which is culmen depth and length and flipper length. So if we look in this figure, that's the flipper and that's the culmen that we are talking about. So a good machine learning model, what it would do is instead of us creating the mathematical notation, mathematical formulation, the model in this case, in case of machine learning, would find the weights for each of those features. It will create the model for us if we give it enough data. And so in case of penguin classification, what we are going to use is this, which is a fully connected neural network. And again, this particular diagram is from the docs. So what we have is the body mass, culmen depth, culmen length, and flipper length as the features, which forms the input layers. And then in middle, we have the hidden layers. And finally, on the right hand side, we have the output layer. So in each of the in hidden layers, we have two hidden layers, the one and this is the second one. And each hidden layer has a circle which is called as a node, and each node performs a calculation based on the values or inputs it receives from the previous layer. Only in case of the first layer, first hidden layer, the inputs it receives is directly the feature values, whereas in the second layer, the input that it will receive are the outputs from the previous hidden layer. And finally, we have the output layer, which are the calculated probability values. In this case, there are three different classes of penguins, so we have three different values calculated, and they add up to 1. 0.02 plus 0.95 plus 0.03 would be 1, and the highest probability is to the class chinstrap. That is to say that that particular uh, row or that particular record was processed by the model and it calculated these values, and therefore because there is a highest probability that that particular uh, record as for chinstrap, we can classify that record as a penguin who's which is a chinstrap. So the measurements that we ran through the model gave us a probability of 0.95 for chinstrap can be classified as a chinstrap penguin. And as we'll go through this course in further videos, we'll see different types of other neural networks that can also be used and what are the pros and cons of that. For now, we'll proceed with building a Keras model for this fully connected neural network. Create a model using Keras. Here we'll use the sequential model
And in previous videos, we did write the module from scratch. Here we'll use the inbuilt dense layer that is in Keras. For that, we'll create a variable model is equal to tf.keras.Sequential, and within open close parentheses, open close square brackets, we specify the layers. So the first one is tf.keras.layers.dense, and here we'll specify 10 nodes, and activation is equal to tf.nn.relu activation function, and this is to bring non-linearity into the model so that it is able to find that relationship between the features and the labels. Is equal to input shape, and we have 4 features. So we have the body mass, then the Kalman length and depth, and we have the flipper length. And next we have keras.layers.dense, and in this case again we have the second, so in this layer we again have 10 nodes, and we can have the same activation function tf.nn.relu. Now the input shape for this is going to be same as the output shape of the dense layer. So we need not specify input shape for this. Next we have tf.keras.layers.dense, and in this case we have number of node units is 3, and that is because the labels that we just have 3 unique labels. That is 3 types of penguins that we are trying to classify, and that's why we just have a 3 there. Now when we run this we now, okay, so there's a typo. um, Activation, of course, that's my mistake. So with this we have now successfully built the model. We can now use this model to before training, if we just want to see how the model works without training, let's create some predictions. So predictions is equal to model, and we can input some features. And when we look at this, so if we look at the features, these are the features we have: 1 2 3 1 2 3 and 4 columns, and that's representative of the input shape we have 4. And when we get the predictions, so predictions, and we look at 5 of these, the output we should see these are the values. Now if we add these up, they do not add up to 1, and that's because these are logits. We need to convert it to the probability for each class using softmax function, and that can be done by simply saying tf.nn.softmax, and inside of the parentheses we can specify predictions, and then get the 5 values there. In the output we now have the probabilities. So for this record we see that if we add these numbers up, so this would be a plus here, and there would be another plus here. When we run this adds up to close to 1, and so these are the predictions. So looks like this is way uncertain, so this is saying that probably belongs to this particular class where the probability is higher. If we now print the labels for these, so we can do that. So we can say tf dot for each of these rows we can pick the max value and print that. So predictions, we can say print prediction, and here we can put the curly braces, comma, dot format tf.math.argmax, argmax, and here we have the predictions. uh, Predictions comma axis is equal to 1, and okay, so we have that, and then we have print labels, and again labels, we can leave some space down here so that the labels are exactly on top of each other. Dot format, and here we put the labels. Now when we run this, we see here that the labels that we have, most of these have come up as 0, whereas the actual class is different, and that is okay because the way we have tried to get the predictions is without any training, and we would expect that the output is not going to be accurate. And so this is just to show that we created a model using layers, sequential layering in Keras. We looked at the predictions, we looked at the logit values, we are able to convert the logit values into probabilities using softmax, and then we also looked at what are the predicted classes in this case. Next step, what we'll do is train the model. Train the model. So what we'll do here is first we'll define the loss and gradient function. So inside of this, define loss and the gradient. So for loss, we can use the tf.keras.losses dot, and here we'll use the sparse categorical cross entropy, sparse with capital S, categorical, and we have cross entropy, and from underscore logits is equal to true, and then we can save this in variable loss underscore objects is equal to this. So that's our sparse categorical cross entropy. And now we'll define a function loss df loss is loss, and then inside of here this takes the model, x values, y values, and training, and then we have y is going to be equal to model, and this is going to be the model that we have above, model comma inside of parenthesis x comma training is equal to training. And here what the training is doing is if there are layers with different behavior during training versus inference, then uh, we need to use this, otherwise we do not need. So in this case we are specifying that, and the function will return the loss. So loss underscore object, we can really loss underscore object, and then we can specify y underscore true is equal to y. So those are actual labels, and then we have predicted labels. y underscore pred is equal to y underscore. So these would be the predicted values that we have above, and with this function we can now calculate loss. L is equal to loss, and we can input model, features, labels, and training is equal to false, and then we can print the loss, and loss object is not defined. Oh, that's because I have extra s there. And when we run this, we have the value calculated for the loss, which is 1.0586704, with next step, what we'll do is we'll calculate the gradient. So that can be used during the training. So df grad, and this also takes in the model, inputs, and the target. And with tf dot gradient tape as tape loss underscore value is equal to loss model inputs targets training is equal to true, and this will then return loss value tape dot gradient loss underscore value comma model dot trainable underscore variables. And so this is the function that will work for the gradients. After this, what we need to do is create an optimizer. So let's do that. Optimizer, and we can create a variable optimizer is equal to tf.keras.optimizers.sgd. So that's the stochastic gradient descent, and we can specify the learning rate. In this case, let's put a 0.01, and that's our variable optimizer. And we can then look at how a single training step would work, single optimization step would work. And for that, we'll use these values. So loss underscore value grads is equal to grad model features labels, and with this then we can print optimizer dot iterations dot numpy, and we can also print. So this is going to be the step. So let's put a step. So that's the step, and then we also have the loss. So initial loss, and this is going to be loss underscore value dot numpy. And when we run this, we see that step 0, we have the initial loss, which is 1.05. And now we are going to use the optimizer. So optimizer dot apply underscore gradients zip grads model dot trainable underscore variables. And once we have this optimization step, we can again print the same thing. So we can copy this print statement right there, put it down here, and now we have the optimizer dot iterations dot numpy, and then we have the loss. We need to calculate the loss right here. So I'm going to remove just that part and type loss, and then input is going to be model features and labels, and we'll specify training is equal to true in this case because this is going to be the optimization step. And in the output we see that the loss is now we have the loss for this step 0, and we have the loss for step 1, and it is slightly less than the step that we had, the initial loss that we had earlier. With this all set up, we are now in the position where we can write a for loop and perform the optimization. So for that, we will write the training loop. So training loop, and here we need to create some cells. So first thing we'll do is to maintain the history. We have the train underscore loss underscore results is equal to create an empty list there. Then we have train underscore accuracy underscore results is equal to another empty list. So this is all set up. And then we'll specify number of epochs is equal to, let's say, 201. That's because that's what is used in the docs. And now we can create the for loop. So for epoch in range number of epochs num underscore epochs, and here we can specify the epoch underscore loss underscore average is equal to tf.keras.matrix.mean value, and then epoch underscore accuracy is equal to tf.keras.matrix.sparse categorical cross entropy. Sorry, my mistake there. This should be categorical accuracy. Okay, so we have those calculated, and then we are going to perform the training in batches of 32 records. So training loop using batches of 32. So for x comma y in ds underscore train underscore batch, uh, the first thing we'll do is optimize the model, and within this we have loss underscore value grads is equal to gradient model. The input is going to be model x comma y, and then we use the optimizer dot apply underscore gradients, and this will have the zipped values for gradients grads comma model dot trainable underscore variables. So that's going to be the part for optimization, and then we can uh, look at the history that we can track. So epoch underscore loss underscore average dot update state, and we are going to update it with the loss value that is calculated above. So that's the current batch loss, and then we can also update the accuracy epoch underscore accuracy dot update underscore state, and then we have y comma model x comma training is equal to true. So with this, we are now calculating and updating the values for loss and accuracy both. And finally, so end of epoch, you have train underscore loss underscore results dot append epoch underscore loss underscore average dot result, and train underscore accuracy underscore results dot append epoch underscore accuracy dot results. And with this, then we have appended the loss and the epoch loss and epoch accuracy inside of the empty list that we had created above. So if epoch mod 50 is equal to 0, so if the remainder is 0, that is to say we have the epoch mod 50 is percent 50 is equal to 0, then we want to print an output every those number of statements or those many epochs have passed by. So we can say epoch. So we have the epoch, and again we can specify this in the number of floats we need. So epoch open close curly braces and 0 3d, and then the next thing we have is the loss. Again this you can put in curly braces colon, so we just need three decimals there, and then finally we have the so let's put colon there, and then finally we have the accuracy, which again we can put curly braces colon dot 3, and then we have the percent sign on. With that we can now write the format and epoch. That's the first one. Epoch underscore loss underscore average dot result, the second, and then we have epoch underscore accuracy uh, dot result open close parenthesis. So with all this set up, I think we are in a position to be able to run this. So let's run this and see what we get. So we have an error. Oh, that's because it's a typo. Results, need a U there. Okay, and so that's again typo, don't need the S. It's a result. And we now see the training in progress. So the first epoch we have the loss value is high, we have accuracy of 74. As the epochs proceed, we should see that the accuracy go up and the loss go down. So by 100 epoch, we see that the accuracy is 80. The loss is reached 0.4, and by end of 200, we see that the accuracy has gone up to 94, and the loss has come down to 0.25. So that's awesome. A classifier can go, in this case, has gone up to the accuracy of as high as 94%. Now it's time for visualization. Visualize the loss function over time. And as I mentioned earlier, this code is exactly copied from the docs, and I'm just typing it out here and kind of explaining what the code is doing. For the plots, what we'll do is we'll try to plot the loss and accuracy over time. So this can be two plots with a subplot. So for that, the syntax is we use a fig comma axis. There are different ways we can plot this. So in this case, we'll use the method that's in the docs, plt.subplots, and we have two, and share axis is equal to true, fig size is equal to 12,8, and inside of this then we have the fig dots subtitle. So title for the both the subplots title, and this is called as training matrix, and below this then we have our axis square brackets 0 dot set underscore y label, and this has the label as loss. Font size is equal to 14, axis 0, and we are going to plot the train underscore loss underscore results. And then axis 1 we have set underscore y label, and here we have accuracy, and we have font size is equal to 14, and axis 1 dot set underscore x label. There's a typo there. We label, and we have epoch. Font size is equal to 14, and finally we have axis 1 dot plot train underscore accuracy underscore results plt dot show. So with this, we should be able to see two plots, and here they are. We see that the accuracy increased up to epoch 25, then it was pretty much the same until it reached epoch 125, and after that the accuracy improved further, and we can see that the loss has gradually decreased right up to the epoch 200 and 200. And there is a typo, just get that done. Okay, so that's how the model, we created a model using Keras, then we trained the model, and after we trained the model, we are able to now visualize how the training progressed through different epochs. Let's now look at how we can evaluate the model's performance. So evaluate the model's effectiveness. And what this means is the model needs to be tested on an unseen test dataset and see how accurate it is on an unseen dataset, because the accuracy and trained dataset is definitely going to be higher, but the objective is to see if the model generalizes well on an unseen dataset. And so for that, what we are going to do now is look at test accuracy. Test underscore accuracy is equal to tf.keras.matrix.accuracy, and we'll use ds underscore test underscore batch is equal to ds underscore test dot batch, dot batch 10, and we'll use again a for loop. So for x comma y in ds underscore test underscore batch, logits is equal to model, and we have x training is equal to false, because we are done with the optimization step. And so whatever weights have been found in the optimization step, we are going to keep those as is. And so we're setting training is equal to false. Prediction is equal to tf.math.argmax logits comma axis is equal to 1. Output type is equal to integer, so tf.int64, and we have the test underscore accuracy. This is going to be prediction comma y, and finally we can print it out. So print test, we can write test set accuracy comma test underscore accuracy dot result, and run this. So what we have here is we have the test accuracy, and we see that the test accuracy in this case is 0.94. So for this, what we can do is we can put curly braces colon 3f and then put another set of curly braces here, and instead of this we can type dot format and then another comma there, sorry, parenthesis there. It looks like, yep. So the test accuracy is 94%, as we can see. Now we can look at the labels, actual labels. So tf.stack, and inside of sorry, this tf.stack y comma prediction, and specify axis is equal to 1. Now here we can see the model predictions, and we see that we have the first one 1 and 1 is the same. The predictions are pretty much close, except here it is a wrong prediction, but otherwise the predictions look good in this particular set of output that we have. In this last part, what we'll do is we'll use the trained model to make predictions on unlabeled dataset. And to make that happen, we'll create a dataset here. Predict underscore dataset is equal to tf.convert to tensor open close parentheses, open close square brackets, and here we'll specify 0.3, 0.8, 0.4, 0.5, and again this example is as is from the docs. 0.4 comma 0.1, 0.8, sorry, 0.8 comma 0.5, and finally we have 0.7, 0.9, 0.8, and 0.4. So these are the values for the 4 features that we have. And of course there is an error, and that's because missing the 2 commas. And we can now use this dataset. Predictions is equal to model, and can input the predict underscore dataset comma training is equal to false. And once we have that done, we can write the for loop for I comma logits in enumerate predictions, and here we have class underscore idx is equal to tf.math.argmax logits.numpy, and p is equal to tf.nn. So we are getting the probabilities for each class softmax from the logits, sorry, open close parenthesis logits, and we have the class underscore index. Name is equal to class underscore names class underscore index. And finally we can so there's a idx and it not so that's my mistake there. This should be idx and not the completely spelled out word. Okay, so we can print now. So print an example prediction and open close parenthesis. We have 4 comma 1 1f, and then we have the percentage sign like so, and finally format I comma name comma the percentage, so multiplied by 100. And when we run this we have an error, so that's because there should be another set of curly braces in here. Okay, so this is what we have, the predicted cross probabilities for these three cases. So the first case, this is classified as ideally with 76% probability, Gen 2 with 98%, and Chinstrap with 59%. And that ends this particular long video on how to build a classifier using TensorFlow and Keras to classify penguins in this case. If you have any comments or suggestions, please do let me know in the comment section below. I hope this particular exercise was helpful to you, and I hope you continue to watch the future videos where we'll discuss some additional projects as we go through this uh, course in learning Keras and TensorFlow. Thank you. Please like, share, and subscribe. Your support means a lot to me. Bye for now.